we've all heard a lot about plate tectonics and continental drifts, but how did these ideas come about, and how did we develop them? So this is also kind of an interesting story because we usually think of science as being totally progressive, and people propose new ideas, and they get enough evidence for them, and once they've done that, their job's done. Everyone should accept it and move on with it and grow from it, right? But that's not the case with plate tectonics. And what you'll usually hear from a lot of people is that when plate tectonics was first proposed, it was called Continental Drift, and you'll hear that Continental Drift was, fatally flawed for a couple of reasons, and it was correctly rejected at the time. Until it's only much later when there was new evidence that the scientific community was able to then accept continental drift. That's not really true. It's what people like to say. I think because saying otherwise upsets their idea about how things are supposed to happen. But things don't always happen the way that we would like them to. So let's talk about continental drift, things like continental subsidence. Okay, so continental subsidence is the idea that land can be flooded and submerged over time, right? So here we have Atlantis, not really a real example of continental subsidence, but one that's provoked a lot of stories over time. It's an interesting topic on its own. But so continental drift as an idea was first proposed by a guy named Alfred Wegener, who had explored the Arctic. He had a doctorate in astronomy, and he worked as a meteorologist and also a balloonist. An interesting guy. This is when you could still do a lot of different crazy things and still be a scientist. And so he came up with and suggested that the continents had drifted across the surface of the Earth way back in 1912. So over 100 years ago now at this point. And so before this, people did not think that the continents had moved. And in order to explain some of the things that Wegener was putting out, people had always previously thought that continents would sink into the ocean, perhaps sink into the mantle, as there were weird changes in the mantle, and they would get dropped. And at other times, they would get buoyed up by the mantle and rise above the surface. And that you could change not really the placement of the continents, but you could still change the relative proportion of water and land. And so even before Wegener's ideas were proposed, everyone kind of understood that there was something weird going on in Earth's history. And they needed to refer back to this idea of things sinking and moving in order to explain it. There had to be some way to make the surface of the Earth dynamic. So Wegener kind of took that dynamism maybe a little literally and made it so that the continents themselves could move. So he saw a lot of correspondences between things that today are separated, right? So there are a lot of different fossils that have been separated by the oceans or in different parts of land and rock strata, things like glacial striations. And in fact, he also looked at not just the fact that there were striations in two different locations, but the actual orientation of those striations, the alignments of them matched up. And he realized that if he put the continents back together in a particular way, you could join all of those areas, right? You could join the disparate and separated fossil groups back together. The rock strata that seemed like the same rock in two completely different places were now together, and these glacial striations also came back together, and even and could even line back up. Right. So now here's a picture of the Earth doing what Wegener wanted it to do. Right. So here we have Africa, South America, Antarctica, India, and Australia. India not part of Asia at this point. And we have different fossil groups, fossil land and coastal fossil animals, and also plant fossils. And when you arrange the continents in this way, these distributions of these animals line up very well and very nicely, instead of being separated by entire oceans or being spread out across multiple continents. So Wegener called his idea continental drift. The idea was that the continents drifted across the face of the Earth. And so here is the Earth today in an illustration from one of his books. Kind of a funny illustration. It doesn't look like what a map would normally look like. So it's sort of an artistic illustration, and I rather like it. It's unusual. There's something unusual about it. It's very angular. So this is a figure from his book showing the continents separated, and then showing them joined together. So the Atlantic Ocean is here, and at one point, what Wegener is saying is that the Atlantic Ocean did not exist. The Atlantic Ocean had a birth, and it had it had a birth. It's still around today. So it had kind of a life cycle. So this is avant la separation. I don't know why it's in Spanish or something like that. But so before separation and then after, right? And so you have to admit that the outlines of especially South America and Africa really do seem like they go together. And everyone at the time kind of agreed with that, but they thought it was coincidence. And they would point out to other continental configurations that didn't seem like they would fit together all so well. Does North America really fit so well into Europe here? You've got to squish things around quite a bit. So he's kind of held the old world, Africa and Europe, stable and kind of distorted North America in order to get that. In fact, the distortion is very weird because he, if you look here, what happens to the southern cone of South America, it actually wraps around Africa. And so I don't know why. Maybe he thought that Madagascar was once part of it, or something like that. But so anyway, so now here is the current configuration of the planet, of the continents, and these are places in white where you have glacial striations, right? So we kind of know that there were these things called ice ages in the past, and that there were times where there were ice sheets and glaciers. And scientists at the time, especially Arctic researchers, understood that. So in the Arctic they don't have ice sheets, but in Greenland they do actually have ice sheets. That ice sheets could affect the land around them, and they could leave lots of different traces, signs of their past presence. And so a lot of evidence for glaciers were in these areas. And that's really weird because this is the tropics. India is rather warm. Southern Africa is rather warm. Australia, South America, they're warm places, right? So why are these, why is there any evidence at all for glaciers' presence in the tropics? It kind of doesn't make sense. You're not going to have glaciers at tropical latitudes. So now just remove all these continents and imagine that you just have lines of latitude and longitude going here along the equator and offset from it above and below, north and south. You just don't expect there to be glaciers, only at the highest mountains, right, where things can get cold. So a lot of things here don't really make sense, right? The latitudinal organization and everything else. And then when they started looking at this evidence, and now Wegener was not the only person looking at this, right? He did not travel to all these places, and he did not observe all these field sites and find all these different evidences. The researchers in South America and the researchers in Southern Africa and India and Australia were the ones that were doing this. And they were very familiar with this evidence because they could just go right out to the field locations and they could convince themselves of it. They could see the information and really understand it. And so when they look at these signs of glaciers, they not only saw that they were in the tropics, but that the glaciers had actually moved in the direction that these arrows show, which again is very strange because I don't know about you, but I would expect that if an ice sheet starts forming, it'll start in the middle of a continent and it'll grow out from there, right? I don't expect glaciers to start at the beach, right, and then come in. But that's what this is showing, and that was very baffling. And what Wegener and other people did was they said, let's take this data at face value. It must mean that things were oriented quite differently back in the past. And so when you rearrange the continents all in the way that Wegener had proposed, this glacial data all makes sense. It starts off, you have a large supercontinent. The ice seems to start in the center of it, and it grows out from it. And then perhaps this supercontinent was at a more northern more polar position, whether it was the North or the South Pole, right? So it had shifted not only around each other, but then across the face of the Earth to different latitudes. So Wegener proposed that the continents were all at one point together, and he called that togetherness of the land Pangea, all land, right? And so he made up that term. And then he didn't just say that it then exploded into all the continents that we have today. He said that it slowly broke up. And so he came up with the term Laurasia for one of the first divisions of Pangea. So you can kind of see here that Pangea, it breaks up along this line into Laurasia and Gondwana land, which is what we call it now. And as it does so, it opens up this seaway, and that seaway it grows into an ocean as they move further and further apart, is called the Tethys Sea. Well, on this side, it's called the Tethys Sea, and then we eventually get the Atlantic Ocean over here. Now, the Tethys Sea, the Tethys Ocean, is not one of the oceans on the continents on the globe now. If you look at a globe, you'll see the Atlantic, the Pacific, the Arctic Ocean, the Indian Ocean, and then the Southern Ocean. You will not find the Tethys Ocean, although it used to be here. It's been closed up as Africa, as India has collided with Asia. So this is Pangea during the Permian around, it's very hard to read this, but around 200, I think it's going to be very hard for you guys to read it, but it's around 223 million years ago. And then 30 million years later, in the Triassic, at 200 million years, we have this Laurasian and Gondwanan distribution. And so this is really important. I mean, if you're a person that studies paleontology or the history of life on Earth, we know that there's lots of Gondwanan animals and there's lots of Laurasian animals. And so, for example, primates primates are one of the primates are found in both Asia and North America. So the earliest primates are actually found and most abundantly found in some ways in North America, because North America and Asia, Europe, used to be connected, and they slowly drifted apart, and there were many connections between them and many opportunities for the animals to move back and forth. A group of animals is called a fauna. So the Laurasian fauna included the earliest primates, and they had a Laurasian distribution. Separately, the Gondwanan fauna, because they were separated very early on, way back in the Triassic, they developed into their own kind of species, their own kind of animals. And so we actually see a relic of this today when we look at Australia. Australia has marsupials in it still. And that's because in the Triassic, when Pangea broke up, the animals that give live birth were able to do best in Laurasia. They took over Laurasia. And the animals that produced these kind of almost larval forms of mammals, these marsupials, they maintain their dominance in Gondwana land. And also the monotremes, which are things like the platypus and echidna, they're mammals that lay eggs. They would have had, potentially a distribution across the whole world, across all of Pangea. But then as the continents rifted apart, they became restricted to Gondwana land. The ones in Laurasia eventually went extinct. And so even to this day, that separation is still maintained. In the case of Australia is where the marsupials are still in charge, and even the monotremes still exist. So for a lot of reasons, this is really, really, important stuff in a way. So continental drift is what he called this idea that the continents are moving across the face of the Earth, and it was rejected. And it was accepted by some geologists in the southern hemisphere, especially South America and South Africa. And people rejected it because there was no causal mechanism. So it seemed to fit with the data, but he was talking about giant portions of the Earth sliding across one another and over the surface of the Earth, which would, no matter what's going on, take a lot of power. And no one could think of any power source for that. And so he was proposing too. So now plate tectonics is a little different from what Wegener had talked about. He was saying that the continents, these granitic continents, were moving over the top of basaltic crust, oceanic crust, and they were actually dozing through it, plowing through it. So even more power is needed to do that. And so Wegener kind of, he recognized that he needed to have an explanation for it too. He kind of thought maybe it had something to do with the spinning of the Earth. You can kind of imagine like a top spinning and it has some things on top of it that might start moving in all kinds of directions, even opposite of the direction of spin, which sometimes happens. He thought that was a way to kind of get the energy needed to physically move the plates. And she's shown here in some, wonderfully absurd Arctic getup, because he was, again, an Arctic explorer. So people rejected Wegener's continental drift, but they still needed to explain the major features of the surface of the Earth. And so in order to explain it, they came up with and formalized something called Geosyncline Theory. And so this was what everyone was taught up until the 70s. It was only in like the 70s in like the graduate programs of the geology programs that people started looking at continental drift and what became to be known as plate tectonics again. But in the high schools and for undergraduates, it was, even in the 70s, still being taught as geosyncline theory. So what is geosyncline? So the idea here is that the Earth is cooling over time, which is something that we expect, right? And that I've talked about before. So the cooling of the Earth in this idea should result in a contraction of the Earth. As it gets cooler, it crumples down into a smaller and smaller volume, right? It kind of deflates. And so that crumpling of the Earth's crust produces the geosynclines. The down plunging portion of the down folding portion of it is the geosyncline itself. And the geosyncline can then subside further and further into the ground and become filled in with water, and you'd have a subsiding continent then, right? And so now you have this ability to pop up continents where you need them, allow animals to cross them, drop the continent away, and the animals are now separated. So you could have a land bridge between Africa and South America, and that allows all the animals to cross it, and then the land bridge disappears and keeps them. And now we have this disjoint distribution of these animals, or plant fossils, or anything else. Doesn't really work too well for glaciers. I mean, I suppose they would have to say that off the shore there was a high elevation that produced the glacier, and it ran into what today is the coastline. So now this geosyncline theory could kind of explain those things, and it could also explain a lot of other things, right? So when people started looking at in North America, you would have the Appalachians, for example, close to the East Coast, and then when you cross over the Appalachians and you go further west, you start getting deeper amounts of sediment. And so the idea was that the Appalachians are the up part of a geosyncline, or the up part of a fold, and then on going west, you have this down plunging portion, and that basin now can fill up with sediment, and it allows you to now build up a thick layers of sediment that can collect fossils and build up strata of rocks and all kinds of things. So it seemed like a very productive set of ideas. And so it was developed in the 1800s. So this was not only in response to Alfred Wegener, it was but it was what was used against Alfred Wegener. So it was developed in the 1800s by James Hall and James Dana, James Dana is like a famous mineralogist, as famous as a mineralogist can be, I guess, but who developed a system of classifying different minerals that's still used now to classify minerals. So I should have probably shown this picture first, but so we have our uplifting part, we have our down plunging part of the fold, and it can fill in with all kinds of material. It can also then be intruded by lava, and so you can explain and you can map out, and you can get a real map of the North America or other places, and you will see these features. These features are real. These folds that are filled in with sediments are real. People were not making this stuff up. The data was correct in a way, but the interpretation is what was wrong. The science was wrong about it. So it explained a lot of observations about the world, in particular how you get mountains and things like that. It was used as a way of explaining the building up of mountains. Especially, you would have this as you're building up these in one area, you would have another area dropping down. So it was seen, that relationship was seen very often where mountains had basins associated with them. At least in the parts of the world like North America and Europe where most of these researchers were working. So it certainly explained where they were very well. So this was seen, so this was rejected eventually when we get to the 70s and we get plate tectonics. And even then, a lot of the older, the professorial generation of geologists, the people that were teaching these grad students, were seen as people that were clinging to a model that really didn't work with the data, and that they should have dropped because of these improved hypotheses of plate tectonics. So what were some of the things that changed between Wegener's time and when plate tectonics was accepted, right? So the people that brought about plate tectonics didn't necessarily consider themselves to be students of Alfred Wegener or promoters of his idea. Like I said, most people agreed and believed that his ideas were properly rejected, even though they really weren't, right? It lacked a causal mechanism, but so what? Does the idea that the Earth is cooling and crumpling work as a better causal mechanism than that justifies rejecting plate tectonics? It doesn't really make sense to say that. It was rejected for a lot of other reasons than that. But the new data that ended up convincing everyone comes in a couple different packets. And so one set are when people started doing sonar studies of the ocean floor. And it's kind of interesting too, because all this is tied in, a lot of this in fact is tied into World War II. So in World War II, people had developed this idea of a sonar, and they used it to look for Nazi submarines, to look for shallow areas, shoaling areas that a ship or submarine might run into, perhaps. But they also realized that these sonar waves, these sound waves, it would ping from the ship or be sent from a ship and bounce off an object, whether it was another submarine or the ocean floor. They could be used to map out the ocean floor. Sometimes the sound waves penetrated the loose sediment that was at the bottom of the ocean and then bounced off the harder basaltic crust. So then you can get an idea of how thick the sediments were, and you could see changes in sediment thickness. And it also showed the existence of things like mountain ranges under the oceans. And so that's kind of shown nicely here. So here we have oceanic crust. We have a layer of sediments. And people started finding that it was thin, close to. They found these ocean ridges running across the oceans, and they realized that the sediments were thin at the ocean ridges and thick at the ocean crust. So this is not something that one person did, and one study was done at one location, right? If you do this, if you do something like that, you'll never find out what's going on, because you'll take some measurements, and maybe it'll be a little bit thicker than normal at that part of the ocean ridge. And it's a little bit thinner as you get further away than it would normally be for some odd reason. Maybe there's a current blowing away the sediment there. So it had to be done en masse. It had to be done in a lot of places at a lot of times and studied by a lot of people. But the original studies that at least suggested these things were done on military boats in the middle of the war, of World War II. So in particular, Harry Hess is associated with this. So Harry Hess was a captain of a ship called the Cape Johnson, and he did a lot of these sonar studies, and he realized that this data that was coming back to him from reports from other people on the ship, from his workers on the ship, was useful for more than just hunting submarines or steering the ship. So this was totally unplanned. It was in the middle of a war, but he did this scientific work anyway, right? In the midst of doing everything else. And so he also discovered something. So he collected a lot of data about this, the kind of things I mentioned. He also discovered that there are a lot of sea mountains that have flattened tops, right? So instead of being peaked under the ocean, they're flat. It's like their tops were cut off. The tip of the mountain was cut off. And then they had sunk under the ocean too. So he called these things guyots. And he realized that the guyots also increased in depth the further away you got from things like mid-ocean ridges. So in the middle of the ocean, the guyots were relatively shallow, and then they got deeper and deeper and deeper as you got closer to the coastline, which is almost the opposite of what we all would naively expect to happen in the ocean, right? The further out you go, the deeper it should get, right? It's the opposite for a lot of this stuff. Okay, so that was sonar studies. There were also geomagnetic studies. There were people that were looking at using magnetic instruments to, again, hunt for Nazi subs or anything else like that. And but they realized that so in order to do that, so they would have a device on the ship called a magnetometer. And all it would really do them is tell them about changes in the strength of the magnetic field that the ship was passing through. And so they had to really know if they were in an area that had a heightened field or a weakened field. Because if they were in a place that had, they wanted to know what the background field was, basically, so that they can then detect metal ships moving around them. So they had to really have a good idea and start mapping the magnetic field in different areas. And so you can kind of think like there's a general magnetic field everywhere, and then there are deviations from it. There are anomalies. There's places where it's weaker and there's places where it's stronger. And so they would have to keep track of these magnetic anomalies. So they found drops and increases in the magnetic field on these ship-mounted magnetometers. And so they created these maps of seafloor magnetic anomalies. So here is one in profile, in cross-section. So here is a ocean ridge, and as they approached the ridge, they would see differences in the magnetic field strength. No big deal, right? It changes over time. Who knows what's going on? The rocks here are a little more magnetic. The rocks here are very unmagnetic, right? And then they get to the ridge. They didn't care. They were still crossing the ocean. And then they saw more changes. But then they realized those changes are identical. They're symmetrical. There's symmetrical changes about the ocean across the axis of the ridge. And so now that's a cross section. Here it is in map view, like you're looking down on it. And so the symmetry is to some people even more obvious. So here's the ridge. And as they get away from the ridge, there's changes in the magnetic anomaly. And they see that same pattern more or less over here. And notice also these differences are aligned with the ridge too. They parallel the ridge, right? So now that's another advantage of looking at a map view instead of a cross section. They get these long linear features. Why should it be like that? Why should there be stripes that have the same magnetic anomaly? I mean, it makes sense that there's little blobs in places that have all kinds of different patterns. Well, why does it match the ridge so much? Very, very odd. And so what are these ridges? So here is a map of a map showing the relief, the topography of the ocean floor, and it shows the Mid-Atlantic Ridge, which is a mountain chain that runs across the middle of the Atlantic Ocean from Iceland down into the southern Atlantic. So so this pattern is very strongly associated with the ridges and mirrors them. And now here's another picture showing that pattern where the ridge is near Iceland. And we also have this profile. So now we have the map view and also a profile showing the seafloor surface. And so we have this this ridge that is a shallow area because it's a mountain under the water rather. And then the land gets deeper as you get further away from it. And also shown in the middle of this ridge is a little divot, and it runs across the whole up and down the whole ridge. This is called a central rift valley. It's not just that there's a mountain chain. The mountain chain actually has a valley within it. So in some places the magnetic field was stronger, other places it was weaker. So how do these rocks even get any magnetism, right? How is there anything going on with that, right? So if you in a lab melt a rock and then let it cool, it will pick up the magnetic field that it's in. And so you can use a magnetic device to artificially create all kinds of magnetic fields in molten rocks. But once the rock is frozen, once it's solid, you can't change its magnetics anymore, right? It's not easy to change it, rather. This is because the atoms are able to freely move in the magnetic, in the molten liquid, and they're able to align with the magnetic field that they're in. So if it's pointing one way or the other, they align with it, right? So that's what happens in molten rock. And so now people have to kind of take that idea from the lab and start trying to apply it to this pattern that you see across the ridge. So it implies that the rocks were molten and took up this pattern. Now, there's lots of ways you can do that, right? Maybe this whole entire field was molten, and there was some weird sort of magnetic anomaly that created a very unusual and linear magnetic field. They alternated, or who knows what. There's all kinds of explanations you come up with, right? But so, because of the lab studies too, people were able to say these magnetic anomalies detected on our boat in this instrument are actually a result of something happening in the rocks. It's not the ocean. It's not that the magnetic field in this location is weird. It's the rocks themselves that are having an effect. So so that's one set of magnetic information. There's also another set of magnetic information that went into this. So people realize that Earth's magnetic field can flip. So we're not talking about the physical North Pole, like Antarctica, the Arctic, or the physical South Pole, like Antarctica, switching places. We're talking about the magnetic field itself, which part is the north and which part is the south part of a magnet is what's being reversed. So you can kind of imagine, I think, that you could have an instrument, a piece of electronics that creates a magnetic field, and that you can dial in any kind of form that you want there, right? So you can have all kinds of weirdly shaped magnetic fields that can flip back and forth and do all kinds of things. The Earth can do some of that too. The Earth's magnetic field flips over time, and so if the seafloor is recording the magnetic field that it's exposed to when it's molten, then it could record times when the polar field has been flipped or is reversed. And if it records, if an area of the seafloor is recording a time when the Arctic had this Earth's south magnetic pole, when you pass over it today, your magnetometer will drop. It's going to pass over a place that has a magnetic field, where the rocks have a magnetic field that is aligned in the reverse of what it is today. So people had to kind of put these things together and realize that the field in the rocks, the signature in the rocks, can be detected by these magnetometers. And so people were also able to start reconstructing. They didn't immediately apply this to plate tectonics, right? Because that idea hadn't even come into existence yet. But they started realizing that they could look at patterns of polar reversals by looking at the magnetics of the rocks that they got. So sometimes they would drill a core for the rock, they retrieve a long sample of it, and they would then start using a magnetometer to measure the magnetic field in those rocks. And you get something like this, showing times of normal polarity, where there's a North Pole in the Arctic, and times of reverse polarity, where there's a North Pole in the Antarctic. And you can kind of see that it doesn't have a regular pattern to it. It's a pretty chaotic pattern. It reverses back and forth quite a bit. Sometimes it's very long periods. Sometimes it's a very short period in which it's reversed. And it's happened a lot. So this is 0 to 1 million years. So even during periods of human history, that the magnetic field has reversed, and there's no it doesn't affect people. It doesn't cause some kind of cataclysm. When we look at the archaeological and anthropological record, you cannot tell that there are polar reversals without looking at this polar reversal data. Right? You have to look at the magnetic data itself. We don't see that there's a decrease or increase in populations or anything like that. Okay, so now, since this is something that's a little bit strange, right? So this chart here shows the current North Pole, and then it shows the North Pole as determined by the rocks at different locations. So you would look at the rocks during, say, so the North Pole kind of it wanders around normally, and it's doing so even today, and that North Pole projects its field everywhere. And if you have some rocks erupting here or melting here and becoming solid, they'll record the North Pole as pointing in this direction, let's say. But then in the past, the North Pole might have been over here. And so the molten rocks that are up then might point to the North Pole as being over there. And so on. So on the one hand, this should be fine, right? The North Pole itself can move around. So when we look at the rock record, we should see changes in where the North Pole is. But when we look at the rocks from, say, 100 million years ago, in this location, it says the North Pole is over there. But then we look at the rocks from 100 million years, 100 million years ago from this area. They say, no, the North Pole was over here. These are two different spots. There's only one North Pole, right? There's not going to be multiple North Poles. So this immediately can't be reconciled. And so so what you're seeing here is all the rocks, the rock record at one location saying where the North Pole is, and then the rock record at a different location pointing to where the North Pole is. They should always be pointing to the same spots, even if that spot is moving, right? Because the North Pole itself can move, but it should never be that, today there are no rocks saying the North Pole is here and the North Pole is also over there. There's not multiple North Poles. So this is called polar wander, but it's really the separation between these North Poles. And so there's no good way to explain this without saying the rocks themselves have been moving, right? The continents themselves have drifted and moved. And so they were originally both pointing, if we have a continent and we have the two rocks, they're both pointing at the same spot. They're saying the North Pole is here. But then one of the rocks gets moved around. And now one's pointing in this direction and the other one's pointing in that direction. And they're saying that's where the North Pole is. That doesn't make any sense. They got to both point in the same spot. It's because of the continents moving. Okay? So this is very strange, very hard to describe, to explain, but for most scientists. But the presence of these magnetometers really resulted in once you have an instrument that you can then start using, people want to use it on everything. And they want to build up all the kinds of data they can with it, right? And if you've got a laser, you're going to zap everything you can with the laser, right? If you've got a magnetometer, you're going to measure everything with a magnetometer. And so they built up this data, and it resulted in a lot of weirdness. Okay, so now Hess also looked at the thickness of ocean sediments, and he found out that there was something like 1/16 the thickness that you would expect if the ocean was 4 billion years old as the Earth, right? Which is so you can kind of, the numbers don't really matter here, right? The point is they could look at the amount of material coming out of the rivers, and then they could say, well, if you have anywhere around that amount, and then you allow that to go on for 4 billion years, you should have a much, much thicker pile of ocean sediment, right? And it's not easy to get stuff out of the ocean back onto land and distribute it somehow, right? Once something gets in a basin, it tends to stay there. So a small difference maybe you could explain away, but this was a wild difference, right? There shouldn't be this small amount of this thin layer of ocean sediments if it's been accumulating for 4 billion years. It implies that the oceans are not as old as the planet, right? And Hess also realized that this cover of sediment thickened the further away you got from the mid-ocean ridges, which is also, very, very hard to explain normally. So Hess suggested that the ocean basins were in fact young and younger than the continents, and that that new seafloor material was erupting at these mid-ocean ridges. And he thought that as this new material erupted at the ridge, it would push old material away, and that old material would get further and further away from the mid-ocean ridge, and it would eventually be where the coastline is now, and it's at these margins that it would then be pulled back down into the mantle. Because Hess realized that if you start growing an ocean, if you start spreading the seafloor out, the surface of the Earth is going to get bigger. You're adding material and you're pushing it out, so it has to all start getting bigger. So he realized that you have to also have some way to get rid of material, and he realized that you could do that by having that older material that's very cold and dense sinking back down into the mantle, either being pushed by stuff spreading or being pulled by other forces. So Hess comes up with this idea of seafloor spreading, right? New seafloor added at the ridges, spreading out and growing over time. And so now as material erupts at the mid-ocean ridge, it records the magnetic field. And then there's more of an eruption, and it records the magnetic field. And then there's more of an eruption, and now it records a polar reversal and a reversed field. And then it records a normal field, and so on. And so you get not only new seafloor, but you explain this linear why the magnetic pattern is symmetrical about the ridge and tracks the ridge. So it explains a lot of stuff. Hess really was spot on with this stuff, right? So the new rocks are also very hot. They're less dense than the colder rocks, so they're more buoyant, so they sit higher on top of the mantle. They're very buoyant. They're like styrofoam. Whereas so they sit high in the water. Whereas the other rocks are very dense and they might sit lower in the water in the mantle, just like a piece of wood sits lower in the water than styrofoam. And so this explained the seafloor topography, and it also explained things like the geodes. So a geo, again, is a mountain. It might have been underwater, and maybe it was high enough that it was exposed above the water, and the waves wore away the top. And now, as the seafloor keeps spreading and spreading and spreading, this material is older and older and older. It gets colder and colder and sinks further and further and further, right? So at one point it was above the ocean, above the water. Its top got flattened, and then it gets pulled down as it moves further and further away from the mid-ocean ridge. It explains a lot of things with this idea. So here's kind of just a picture of that. Here's the something like the mid-ocean ridge. It's being fed by magma. New material is being added here, and it's cooling. It's all being pushed away, and it gets eroded, flat-topped, and sinks further and further. Now here is just some more detail about that mid-ocean ridge. So we have the oceanic floor made of basaltic rock. That sediment pile, which is very thin here and very thick here. Why? Because the rock here is new. It has not been around long enough to build up a thick pile of sediment like this rock, which has been accumulating sediment as it moves along. And at the ocean, at the ridge, at that ridge, there is also this central rift. And it is not the case. I don't want anyone to think that everywhere along the rift there's constantly erupting lava. It happens very rarely. Over the course of geological time, it's enough that it spreads out. This is why it wasn't obvious to anyone what was happening, because you couldn't just go there and see mountains and rivers of lava erupting. And then there's some more details about the structure of the earth and structure of the mantle and the minerals that you find there. And when people started to also, Hess was proposing these ideas, and what other people did was they actually measured, using other instruments, the amount of heat flowing through the seafloor. And they found this pattern. The closer you were to the ridge, the younger the crust was, the hotter it was, and the older it was, the cooler it became. And so this also works to help explain polar wander, like I said. Now these were all proposals and ideas and theories, and later some workers named Vine and Matthews. Their idea was that, well, if magma is erupting at the ridges, then it should record the magnetic signal of the Earth, and this should produce the symmetric pattern. And so they used that as a test for this seafloor spreading hypothesis. So they actually went out and measured all of these reversals and examined them in terms of the seafloor spreading theory. So they were looking for places where you do not find this symmetrical pattern, right? And if you don't find the symmetrical pattern, then that argues very strongly against it being produced by spreading. Okay, so I kind of explained this stuff before. So a lot of what's happening in these ridges and in the seafloor spreading is being driven by something called convection inside the mantle. And so in mantle convection, you have melt that rises at the ridges, it cools, sinks at the edges, and this produces a convection cell. So the typical example that people look at here is like a pot of water. You have a pot of water boiling on your stove. The water is very hot at the bottom. It rises to the top, cools off, sinks back down because it's cooling, it's denser, and it sinks relative to the hot water that's rising. So it's a density-driven process, right? The water gets heated, becomes low density, rises, floats within the pot, right? And the denser water at the top that is cooled sinks to the bottom. And so everything gets stirred up within your pot of water. Same thing's happening in the mantle. You have this convection cell within the mantle, and then the crust is kind of riding along with it, being pushed along with it all, following the same pattern. So this is the causal mechanism that continental drift lacked. And notice things are also pretty different from continental drift. Here are the continents. They're not plowing through the mantle, plowing through the basaltic seafloor, right? They're moving along with it. It's all part of it. So it's now not just continents that are drifting, but it's big plates of the crust made up of continental and basaltic material that are moving, all being driven by this churning over of the mantle. And so mantle convection, the mantle is not liquid. It has partial melt within it. It moves very slowly. It kind of moves. I mean, imagine you have your pot of boiling water, but it's a pot of solid, cold clay that is doing the same thing. So it has this motion while it's still partially melted and partially solid. The continents are rifting apart and the seafloors are spreading. Then either the Earth is getting bigger or some material is being lost somewhere else. And so there was a researcher named Wilson who really looked at this in more detail. And so Wilson came up with what's now called the Wilson cycle. So he realized that as new oceans grow, the old oceans are closing up. And so here is a plate, and it undergoes rifting. It starts getting pulled apart. That convection cell in the mantle is doing its work on it. And the seafloor starts spreading and starts growing. And so now you have one continent, a continent with a large rift in it, and now you kind of have two continents with a growing ocean between them. So this could be South America and Africa right now, with the mid-ocean ridge here. And so now the Atlantic is growing. And like when people like Hess first thought of this too, they thought maybe the basaltic material was being pulled down at the edge of the oceans. But as it turns out, in most cases, what's happening in one ocean affects another ocean. So the seafloor spreading here in this growing Atlantic Ocean, for example, you kind of have to imagine that this block is now over here. So we have the Atlantic and Pacific Ocean. As the Atlantic grows, it starts pushing the continents here, right? It's moving this way, it's moving that way, and it pushes them into towards another continent, and it starts closing up an older ocean, and that ocean's seafloor is subducted or dragged down beneath the continents, and it's able to be subducted because it's dense and cold material. So if it's more dense, it can sink relative to the other one. And as that goes on, the older ocean gets smaller and smaller until the two continents crash into each other. The ocean's no more, and the two continents are sutured together and perhaps grow amounts in between them. So this is the Atlantic right now. This is the Pacific right now, where there's lots of places of subduction. This is the Tethys Ocean that I talked about earlier, as India and Asia start to collide. And when they do actually ram into each other, the Tethys Ocean is lost. And you start building the Himalayas and things like that. So these pictures could all be different ocean basins at once, right? Like the Atlantic and Pacific. Or you could say, this is the Atlantic Ocean now, and this is the Atlantic Ocean in the future. Eventually, that seafloor spreading is going to run out of steam, and some other ocean somewhere else is going to be rifting and start pushing the Atlantic closed. And it's going to produce, it's going to result in the end of the Atlantic Ocean. The oceans have a birth with rifting, and they have a death with continental collision. And this cycle of birth and death is called the Wilson cycle. And so Wilson, like I said, he was a researcher, and he came up with a lot of these ideas when he just took pieces of paper, cut them kind of into the shapes of continents, and started moving them around and playing with them. And so it's a very basic, almost goofy type of modeling, but it is a model of the Earth. It's not an advanced computer model, but he was able to model the surface of the Earth using pieces of paper like that. So Wilson and other people, so other colleagues of his, they're the ones that brought together continental drift, seafloor spreading, mantle convection, and everything into what we now call plate tectonics. And so this is a map of the Earth, and what you have here are the different tectonic plates. Here's the North American plate, the Eurasian plate. We have lots of places where there are smaller plates, like here's the Scotia or Nazca plate. Here's the Arabian plate. The Caribbean plate is here. Okay, and now this is very simplified. A lot of these plates are actually made up of many, many smaller microplates. And so here we have the mid-ocean ridge cutting through Iceland. You can actually go to Iceland. You can see the ridge, the Rift Valley in Iceland, and it continues. It runs across the whole island, and then it just sinks under the ocean. So you don't have to dive to the bottom of the ocean to see this. And the mid-ocean ridge runs along all of the Atlantic. So there's lots of smaller plates that make everything up. People like Wilson were saying that the plates were very rigid. That means that when they would crash into each other, they couldn't flex and bend, and they couldn't bounce or anything like that. We kind of think things are quite different now. But importantly, the plates are riding, the crustal plates are riding on top of not water or liquid, but the asthenosphere, which is very weak and can be deformed pretty easily, and it's where that convection is going on, and it's that convective motion that's driving all of these plate tectonics. So this means that plate tectonics has a lot of explanatory power. There's a lot of things about the Earth that it can explain. There are some things that it was kind of made in response to, like Wegener's data and the seafloor spreading magnetic data. And then there's other things that it wasn't really made to explain, but that it does, like the distribution of mountains and volcanoes and earthquakes. So, like I said, Wilson had pieces of paper that he was able to move around relative to one another, and he realized pretty quickly that, especially because they're not pieces of paper moving all over in space, right? They have to all kind of move on the same plane. That there's only a couple things they can do, right? They can run into each other. They can go away from each other. They can also slide past each other. Maybe that took a little while to figure out, right? So there's only a few types of plate motion, or rather plate interactions at the boundaries of the plates. There are convergent boundaries where the plates run into each other. There are divergent boundaries where the plates are moving away from each other, like at a ridge, at a rift. And there are places where the plates are sliding past one another, called a transform boundary. So there are convergent, divergent, and transform boundaries. Okay? Now, you can have a couple different types of convergent, divergent, and transform boundaries based on what materials are running into each other. So we can have an individual plate can be made up of continental and oceanic crust, but at the place where two plates are meeting, at that zone where there's an actual interaction, it's probably one or the other, right? So you can have a continental ocean boundary, right, where a continent is running into an ocean crust, and that can produce a subduction zone. You can have two oceanic plates running into each other, and that can also produce a subduction zone. Or you can have two continents run into each other, and that will produce mountain building. And so here you have an example of each. And so here is the subduction where the colder, denser oceanic material is being subducted and sinking relative to the lighter, granitic, less dense continental material. Here you have two oceans running into each other. So now this is an example of this. This is the boundary between plate 1 and plate 2. And plate 2 over here is made up of oceanic and continental crust, like I was just saying. But at the place where they're meeting, it happens to be ocean. The older ocean crust is going to be denser and colder because it's lost heat more over time. And so it's the one that's going to subduct. And now, in both cases, as this material is subducted, it starts getting put under weird conditions. High pressure, it's underneath a mountain. Tremendous pressure on it, right? It's being crushed. And with that pressure comes heat. And with that pressure comes an instability to the minerals that are present. So if you take ice and you heat it up, it'll melt. If you take ice and squeeze it, it will actually melt because the water is not stable at that pressure as ice, as a solid. the minerals that are here are not stable as a solid at those pressures. So they'll also become melt. They'll turn into liquid. And in fact, some minerals are more susceptible to melting under pressure than others. So anyway, as this plate gets subducted, it melts, rises to the surface, and forms a chain of volcanoes that parallels the plate boundary. Same thing here, except this chain of volcanoes is present not as volcanoes on land, but as volcanic islands, as an arc, a linear feature on the curved surface that is made up of volcanic islands. And here we have continent-continent collision, where the materials are being crumpled together and crushed. And basically, you have some of this material is getting shorter. So instead of being very wide and long as it's put together, it gets shorter and shorter. But it doesn't just perfectly stay flat. As it gets shortened, it doesn't lose its length so much as it just loops that length around, and so you can start building up some rather high mountains with this shortening. So in a continent-ocean collision, we have subduction, we have a trench that forms, and we have something called a volcanic arc that forms with some land in between them in something called a four-arc basin. So here's the Juan de Fuca plate going underneath the North American plates, and it's going through a shallower sinking here than in the other pictures. And that Juan de Fuca subduction results in volcanism, and it's what powers some volcanoes, such as Mount St. Helens, and in fact, the entire coastline of North America and South America is a mountain chain called the Cordilleran Arc, that is formed by subduction along the west coast of both continents. So these are some materials that have been caught up in that subduction. So this is actually deep ocean material that has been pushed onto the continent as the oceanic crust was subducting. So and it kind of was scraped off the subducting crust and left as like a block. So don't need to worry too much about that. This is Japan over here, and this is the Nankai trough or trench. And so there's subduction here also. And as that material is being subducted, it kind of bends down at first and produces a place where the ocean is much deeper. Sometimes that gets filled in with sediment. Now over here is another picture of the Nankai trough. It's like a 3D image of what's going on inside of it. So this is used with a lot of seismic analyses. So we send sonar rays or sound waves through the sediment, and we can pick up the boundaries of different sediment layers. Here they're very nicely structured, and then they get a little more chaotic. And they're rather different here than they are over here. And so what you're actually seeing is the boundary between two different plates, and then this wedge, or sometimes called an accretionary prism, of stuff that is being scraped off the subducting plate and left on the overriding plate. And now, so that's a 3D image of that, which is kind of neat. And if we go back to this picture so this is the west coast of North America, we actually have a lot of things that have been scraped off previous plates and added to the continents. So subduction is kind of weird. Subduction is how a ocean dies and is shortened, okay, as the material is brought down. But as it's doing that, it's leaving and adding material to a continent. And so continents can actually grow through the addition of these weird terrains. They're called exotic terrains that add on to the edges of the continents as subduction is going on. And there might be, very old pieces from a totally different configuration of plates there. Okay, so divergent boundary types, right? We can have is where a continent can rift apart, or you can also be where an mid-ocean ridge is active. So here's Africa. Here's East Africa, and we have the Red Sea, the Horn of Africa, Madagascar, right? So, and then we start getting to Southern Africa. And in this region, this is the Great Rift Valley, or the East African Rift, It's a place where there is a huge valley running across parts of Africa. And so it's not a place where there's constant volcanism. It's not a place where it's obvious that the continent is being pulled apart, but it is. So this rift, this is the production of two new continents, of two new plates, in fact. Africa is being torn apart, and one day there'll be an East African plate and then a West African plate, let's say. And so this rifting, it's actually kind of interesting. Here, the rifting is totally on land. It produces very deep valleys that are filled with some very, very deep lakes. And so it kind of corresponds to something like this stage in this illustration of the stages of rifting. So here a continent is singular and it's starting to be pulled apart. As that rift gets wider, it starts filling with water. It might then get wide enough that the ocean can rush into it, and then it might get wide enough that we now recognize it as having a new ocean. So here in East Africa, we have this rift starting to fill in with water, and it's kind of like these first stages. And then the rift actually splits into two. And here is that linear sea stage that we see, the Red Sea. So originally Africa and Arabia were one continent, but now we have this kind of Y-shaped rifting going on, breaking it up into multiple continents. And so we'll eventually have a seafloor spreading ridge here and a new ocean between the two parts of what was formerly Africa. And so that new ocean is going to grow here as the growing stage of a Wilson cycle. Here I have an example of a transform boundary. This is where two plates are sliding across one another. Nothing too exciting here, except that for us, this is what the San Andreas Fault is. A lot of people like to say that California is going to fall off into the Pacific Ocean in a million years or something like that. It's not. It's sliding along North America. It will one day be where like Seattle is now. And Seattle will, if you come back in that time, you'll see that Seattle is actually very far inland, and that California is now extending into the ocean over there. And in the southern part of the country, it's much narrower. So this material is sliding back and forth. It's a transform type of motion. So here's an illustration of that. So we have this equatorward or southward relative motion of the North American plates, and then a northward motion of the Pacific plate. And so over here we have the Juan de Fuca plate, which we talked about before, subducting underneath it, and that's what this little sign is showing, subduction. And that's what's producing this arc of mountains along the East Coast. But so this part of Los Angeles and California is going to be sliding up this transform boundary. These are two plates that are sliding past one another. Notice here also, so this part of the North American boundary is a transform boundary, but this part is a subductive boundary, right? So we have transform boundary, we have a convergent boundary. So these things probably change over time as the motion of the plates changes. So the plate's motion changes over time. How fast do the plates move? It can vary between 1 to 20 centimeters per year, and it can on average be 5 centimeters per year. There are some ridges that are spreading fast. There are some that are spreading slow. The ones that are spreading fast tend to have a lower profile. They're spreading too quick to build up a large profile, a large mountain. And the ones that are spreading slow tend to build up these steeper profiles, including the Mid-Atlantic Ridge is one of them. So now you can kind of imagine as these plates are moving past each other and sinking past one another, and all kinds of things are going on, that they can produce a lot of motion, and they can produce earthquakes. So subduction implies some motion of the plates and can produce earthquakes. And as these plates are subducting, we can actually look at the depth at which the earthquakes occur, and we can see that some earthquakes have a very great depth. They come from a great depth. And so it's thought that these deep earthquakes are coming from these subducted plates that are still being pulled down into the mantle. And so sometimes if there's enough of these earthquakes, you can actually trace out the shape of the subducting plates. So when we do that, I'll show a picture next, but so these deeper earthquakes, they tend to be around 650 kilometers deep. And but most other earthquakes are occurring around 30 kilometers. So the people that studied this were Wadati and Benioff, and so they realized that these deep focus earthquakes are associated with subduction, and because of that, we refer to this depth as the Wadati-Benioff zone. Okay, so here's kind of a cartoon that's showing that exact same thing. We have the zone in which the earthquakes can occur, or were theorized to occur, and so they're quite deep under these volcanic arcs, and they can go back down very, very great depths as the plate is plunging down. So they're not occurring here, and they're not occurring there, right? Because here and there is no subduction. It's only here that we have the subduction at that depth. So we might see lots of earthquakes all along here at these shallower depths. But once we get to the Wadati-Benioff depths, we only see them trace this figure out. Okay, so now here's an actual figure from a scientific paper showing that. So we have, these are the faults that have been examined by lots of different geological methods. And then each one of these dots is an earthquake. And you can see that there's a lot of them that are at relatively shallow depths. But that we then have many more that trace out this block of subducting crust. So this is around Vancouver. This is around the area that we were just talking about in Western North America, where you have things like the Juan de Fuca plate subducting beneath the North American plate. And just to point things out, we have this accretionary wedge or accretionary prism being scraped off the top of the subducting plate, producing some exotic terrains that are being added to North America, and then it's producing some volcanism along here too. So now, I said earlier that plate tectonics, it was kind of developed to explain both the data and information that Alfred Wegener had found, and also the seafloor spreading data that Harry Hess and Vine and Matthews had found. And so it explained the data that it was built for very well, which is, good. We need to at least do that. But it also provided some explanations for other types of data that it wasn't even thought that it would deal with. So here we have a map showing the distribution of earthquakes and volcanic eruptions. And so these maps, especially this one here, traces out the shape of the tectonic plates. In fact, I think this is maybe volcanism and earthquakes. No, earthquakes and volcanism. But so it traces out the shape of the boundaries of these plates. Not too many happening in the middle of the plates, but it does trace them. And here's that East African rift system. Here's India colliding with Asia. And so we have a lot of earthquakes associated with that. And here is the Pacific plate shown very well. And you may have heard of something called the Ring of Fire. It's not a Johnny Cash song only. The Ring of Fire is this ring of volcanic eruptions and earthquakes that is associated with the Pacific. And so that was something that people had known for a long time, that there was this association, obviously. It's kind of important to know where there are volcanoes going off and earthquakes. But it wasn't understood. And it turns out that plate tectonics offers a good rationale or a good explanation for what's happening. So these are all not just the boundaries of plates, but these are all subductive boundaries. So the Pacific Ocean is dying as the Atlantic is growing, and there's some rifting in the Indian and Southern Oceans too. They're pushing away the Pacific at all around it. Right, it's not just at one point. So we know that there is subduction here. We can look at these Wadati-Benioff zones. We can see the type of volcanism that is associated with subduction, and we can also see the volcanism and earthquakes are just focused in this area. So a lot of explanatory power for plate tectonics. So now I want to look at this kind of neat. These are some illustrations of. We talked a lot about what the Earth looked like as the continents drifted. Did continental drift stop? Is plate tectonics over? No, the planet is still losing heat. It still has a partially molten mantle, and that mantle is still convecting. So it's going to keep going on. The continents are moving. So here's something. Right. Let's look at the pictures. So here's Earth during the early Triassic. We have Pangaea and what's going to become Gondwana lands. We have the ancient Tethys Ocean. We have some subduction over here, so we can look at the rocks from this time, and we can see a lot of these features. I should say, so oceanic crust is relatively young. It gets destroyed. We don't have a lot of oceanic crust from this time. We have continental crust from this time because it doesn't get affected too much, but the oceanic material gets destroyed. So we don't have too much of the ocean from the early Triassic, only what gets pushed up onto land. Okay, that's the early Triassic. Here's the late Jurassic, right? This is well into the age of the dinosaurs, and we have kind of a recognizable North America, a growing Atlantic. Here's that Tethys Ocean. South America and Africa and India and Antarctica and Australia are all still together as Gondwana lands. This is Laurasia, which has Europe as a series of islands. Now we're at the KT boundary, or what now is called the KPG boundary, the end of the time of the dinosaurs, 66 million years ago. Here is why it's the end of the dinosaurs, the Chicxulub impact site, a meteorite impact that wiped out the dinosaurs. And so we have a pretty recognizable North America, but there's a gigantic seaway in the middle of it. We have a recognizable Africa. Europe is still a bunch of islands. Gondwana land is broken up. Africa and South America are rifted apart from one another. Antarctica is just about to completely separate from South America. Australia is still part of Antarctica, and India is its own continent that is moving slowly away towards Asia. Now we get to 50 million years ago. This is the Eocene. This looks very similar to what we have now. Antarctica and South America have separated. We have opened what's called the Drake Passage. Now water from the Pacific and in this part of the Southern Ocean can flow. So actually the water from the Pacific can flow into the Atlantic Ocean, and we now have something called the Southern Ocean. So water can circulate freely around Antarctica, around the gap between Antarctica and Australia, and it kind of takes on its own characteristics as it stays down here. So we have now the birth of the Southern Ocean too. And the Indian and Asian continents are starting to collide. Here's our modern world. It should look pretty familiar to everyone. Here's the Earth in the future, in 150 million years in the future. So here we have subduction. Going back to the modern world, there's subduction in the Mediterranean. There's rifting in Africa. So North America and South America don't look too different. They might be even tilted a bit. Australia and Antarctica have recollided. And Africa and Asia have completely collided. And the Mediterranean Sea is gone. And the person that makes this map, whose name is here, Scotis, he does great, wonderful illustrations of maps. It's very scientific maps projecting. We know what the plate motions are. We know what the directions are. Things can change going into the future, but he projects from what we currently know about these movements, and you produce these kind of maps. This is 150 million years in the future. Here's 250 million years into the future. The continents that had separated from Pangaea have now collided again into a new supercontinent, a new Pangaea. There's been many supercontinents. There's been Pangaea, and the Pangaea was the most recent one. Before that was something called Rodinia. There's many supercontinents, and now there's also one gigantic ocean, and he's labeled it as the Pacific Ocean, but we'll not worry about that. So lots of different, Earth, as I said previously in the last talk, is an active and dynamic planet, and this kind of really shows that, right? A quarter of a billion years, 250 million years, a long time away. Very slow movement for these continents, but they will eventually form another supercontinent, which itself will break up as rifting occurs. So I think that's pretty good for this topic. A lot of interesting things going on with plate tectonics. I really think that going back to Wegener, his ideas were rejected, but kind of wrongly. And the people that rejected them weren't actually as familiar with the evidence as he and other researchers were, but they ignored those other researchers because they didn't come from the same institutions the leading institutions of science at the time. So I think that's kind of an important thing and a good place to end on.